Now that you've seen some different expressions for rate laws and what can affect the rate of a reaction, let's talk a little bit more about mechanisms and the rate determining step of a mechanism. So let me tell you a little bit more about these terms, okay? The whole idea behind a mechanism is to try to theoretically describe what's happening in a chemical reaction, okay? And so even though all of these different parameters for the rate laws, like the rate constants, are determined experimentally, sometimes it's possible to calculate them or predict them kind of by just looking at what you think might be happening in a chemical reaction. So in order to do this, we have to know how the reaction takes place, which is called the mechanism. Okay, and so by and large, most reactions are considered to take place in a series of pretty simple, well-understood events, which are called elementary reactions. And so in this elementary reaction, we typically have a relatively small number of atoms that, or molecules or ions that are colliding with each other to make a product. So the number of atoms or molecules or ions that are colliding with each other is sometimes called the molecularity of the reaction. And as far as elementary reactions go, we only have to focus on 3 different molecularities. Okay? The first one is what's called a unimolecular reaction. And so in a unimolecular reaction, only one thing is breaking apart or rearranging. So I can't really say one thing is colliding with anybody because it's just one thing that maybe is breaking apart or somehow changing what it looks like. Okay? For example, dissociation of one thing into 2 pieces, or sometimes what's called an isomerization reaction in chemistry. The bonds kind of move around. Okay? And so this is a unimolecular process. More common, perhaps, is what's called a bimolecular reaction. So in a bimolecular step, 2 particles are colliding with each other. Okay, bi means 2. It's also possible to have something called a termolecular reaction, where actually 3 particles or 3 atoms or 3 molecules are in the same place at the same time and collide with each other. But statistically, that's kind of hard to do, right? It's pretty rare for 3 things to be in the same place at the same time. Okay, so there are examples of termolecular reactions, but it doesn't really happen that much. So now let me give you a little bit of a theoretical description of a rate law. Okay, most elementary reactions are of a known molecularity, which means I can just look at the chemical reaction and tell you exactly how many things are present. Okay, so for example, if I had something like A going to P, then I can, and I know that's an elementary step, because there's just an A there, I can say that the rate of the reaction is just K times the concentration of A. Or if I have A plus B reacting to give me products, I know there's an A there and there's a B there, so I can just write down for this elementary step that the rate is equal to K times concentration of A times the concentration of B. And the point is that I can have a whole series of these elementary steps, and when I add all of these elementary steps together, I get the overall reaction for the entire process. Okay, and so the point is that the mechanism is really this combination of elementary steps that tries to explain the sequence of events or steps in a chemical reaction. Okay, so let me show you what this might look like graphically. Okay, and so on this graph, we have energy on the y-axis and something called the reaction coordinate, or the progress of the reaction on the x-coordinate. So you can think of reaction coordinate as starting out over here on the left side with the reactants, and then ending up on the right-hand side with the products. Okay, and so maybe what happens is one elementary step takes place, and I get to here. And so one elementary step would be up to there, and what happens there is I have a certain activation energy, EA, for that first step. Okay, and so remember, the activation energy is the minimum energy that I need for a chemical reaction to take place. And so in this example, the activation energy for the first step was pretty small. Okay, after the first step is done, the reaction didn't finish. it really created something called an intermediate. Okay, and so the intermediate is going to then be used in the next step. Okay, and so this point right here is the intermediate, and the intermediate has to then react to form the products. And when I make the products, there's another activation energy that I need for that step as well. And the point here is that the activation energy for the second step is a lot bigger than the activation energy for the first step. Okay? Remember we talked about this earlier. The bigger the activation energy is, the slower the reaction is, or the less likely it is to happen quickly. Okay? And so because I have different steps with different energies or different activation energies, that means that these steps are going to happen at different rates. Okay? The one that's going to happen the most slowly is what I'm going to call the rate determining step. Okay, and so the rate determining step determines the overall rate of the chemical reaction, or kind of in a vernacular sense, right? The chain is only as strong as its weakest link. Okay, I have to wait for the slow step to happen before I can do anything else. Okay, and so whichever step has the greatest activation energy, that tends to be the rate determining step. And so in this case, I would say that the second step is the rate determining step, sometimes abbreviated RDS for short.